Hi everybody. We're going to do another video here on a balancing of a redox reaction, and I want to go through this because this particular example has a couple of little tricky issues associated with it, but I also want to have a chance to go through some terminology in a little bit more detail, so hopefully everybody is comfortable with this idea. So I'm going to go ahead and balance this reaction between permanganate and hydrogen peroxide to form Mn+2 and molecular oxygen. So we're going to go ahead and follow our algorithm that we have for balancing redox reactions. The first step, of course, is to assign oxidation states to everything. So to do that, we have here for the manganese, we're going to have +7. For the oxygen, we're going to have -2. For the hydrogen of the hydrogen peroxide, we're going to have +1. And for the oxygen of the hydrogen peroxide, we're going to have -1. This is one of those exceptions for oxygen. When oxygen is in a peroxide, and you can recognize peroxides because they'll have the general formula X2O2. So for hydrogen peroxide, it's H2O2. In that case, there's an oxygen-oxygen single bond, and that ends up giving the oxygen, each of the oxygens, an oxidation state of -1. All right, so the manganese +2, of course, has an oxidation state of +2, and the molecular oxygen, each of the oxygen atoms has an oxidation state of 0. Okay, so let's take a closer look at this. What we can see is clearly the manganese is going from +7 to +2. So that's a reduction, right? We're gaining 5 electrons as the manganese goes from +7 to +2. But what's going on for the oxidation? We have a couple of options here. For example, the oxygen of the permanganate has an oxidation state of -2, and then it goes to 0 here in the molecular oxygen. Or we have the oxygen of the peroxide with its oxidation state of -1 going to 0, which also would represent an oxidation. So the question becomes, which of these oxygens, those of the permanganate or those of the peroxide, are the ones that are being oxidized to eventually form the molecular oxygen? Well, I guess I'd like to appeal to a little bit of chemistry common sense if I could. The permanganate here has the manganese +7 going to +2. So the permanganate is kind of already busy being involved in the reduction. So then our most likely candidates for the oxygen atoms that are going to ultimately be oxidized would be the oxygens of the peroxide going on to form the molecular oxygen. All right. So let's continue with our algorithm, and I'm going to go ahead and kind of show you my work all at once, and I'll talk us through it. So let me bring my work up. Go ahead, expand it out a little bit. And so here are the two half reactions that we would have. First, for the reduction, the permanganate going to the manganese 2. So I have one manganese. I have 4 O's, so I would need 4 H2O's on the right to balance the oxygens. By doing that, I bring in 8 hydrogens, and we're under acidic conditions, so that puts 8 H+ there on the left. And then to go ahead and balance the charge, I right now have a total of +7 on the left and +2 on the right, so I need to bring in 5 electrons to bring my +7 down to +2. All right, so this half reaction is now balanced. So we'll pause here for a moment and we can see what happened to the oxygen of the permanganate. It actually didn't get involved in any of the oxidation reduction chemistry because it went from MnO4, the oxygens here, again, have a -2 oxidation state. Well, the oxygens here in water also have a -2 oxidation state. So these oxygens of permanganate, they eventually made their way into becoming water molecules within this aqueous system. All right, continuing on, the oxidation. So I had my hydrogen peroxide now turning into molecular oxygen, going from -1 to 0. So I have 2 O's, so those are good. 2 H's, so I need to bring in 2H+ again under acidic conditions. And by bringing in 2H+, I need to bring in 2 electrons minus to balance the charge. The left side is neutral, the right side is now neutral. Okay, so I have my two half reactions, and I'm going to need to combine them, of course, in such a way that the electrons factor out. So that means multiplying my reduction by 2 and my oxidation by 5. So that would become 10 electrons there, 10 electrons there, so my electrons on both sides of my half reactions would cancel. And remember, you want to see the electrons as a reactant in the reduction and as a product in the oxidation. All right, so if I multiply through by 2, I multiply through by 5, and go ahead and add the half reactions together, I would get this overall redox reaction. So I would have left over a total of 6H plus on the left, 2 MnO4 minuses, 5 peroxides, 2 manganese 2s, 5 oxygens, and 8 waters. Let's just make sure that this is balanced. I have 6H plus 10 more, so that's 16H on the left. 8 times 2 is 16. 2 MNs, 2 MNs. I have 8 and 10, so I have 18 oxygens on the left. I have 10 plus 8 is 18 oxygens on the right. 10 H's on the left, plus 6 more is a total of 16 H's on the left. 8 times 2 is 16. And then charge, 6 plus minus 2 is a net 4 plus on the left. 2 times 2 is a net 4 plus on the right. Okay, so I have my reaction balanced. Now what I want to do is I want to talk a little bit more about some terminology. So I'm going to shrink down my balancing of the redox reaction, get that out of the way, and I want to bring up this lingo here, which describes some terminology. All right, so what did we realize? So we saw again that the manganese is the thing that's getting reduced. So manganese is reduced. That means the permanganate is itself an oxidizing agent, right? As the manganese gets reduced, it is taking in electrons, right? You see it's taking in those electrons. Why don't I go ahead and make that a little bit larger? You can see, right, the permanganate is taking in the electrons. So it's stealing electrons from something else. So that permanganate is saying to something else, aha, I'm taking your electrons, I'm oxidizing you, therefore I am an oxidizing agent. Meanwhile, the O in the hydrogen peroxide is being oxidized, right? So the O goes from -1 here to 0, so it's being oxidized. All right, so that means it's giving off electrons, right? It's giving off electrons. So it can then say, okay, here are some electrons. I'm going to go give them to something else. I'm going to reduce that something else. So that makes the oxygen in the hydrogen peroxide a reducing agent. So it's not really particular how you say this. You know, the manganese is being reduced, but the manganese is part of permanganate. So I think it's typical to say that the permanganate is the oxidizing agent. The oxygen is being oxidized, but that oxygen is part of peroxide, so I think it's reasonable to say that the peroxide is the reducing agent in this particular redox reaction. All right, so I realize it gets a little confusing, right? But the thing that's reduced is itself an oxidizing agent, because as it takes in those electrons, it took them from something else, so it oxidized that something else. The thing that is oxidized is itself a reducing agent because as it loses electrons, those electrons are going somewhere else and forcing the reduction of that something else. So the thing that is oxidized is a reducing agent. All right, I hope that clarifies some of the terminology, and I hope that makes you a little bit more comfortable with how to talk about oxidation reduction reactions.